glad to see such a high attendance, but it's not it's normal because we have a very distinguished speaker this week, Tim Davis from the University of Florida, who has spent a lot of his energy developing very clever software for sparse numerical linear algebra. And I know, and I'm sure everybody knows, that most of his software is actually in use in most of the things we do every day. And so today we'll learn more about what's under the hood, maybe.
Well, thank you very much. I appreciate you all coming. So today I'm going to talk to you about sparse matrix algorithms, but really it's just it's graph theory on steroids. It's graph theory plus numerical linear algebra plus applications. So I do span that whole spectrum. Today I'm going to try to condense 25 years worth of work in about 3 hours. My clock does say I'm on Florida time. So I'm going to talk about contributions to the field, some of my current work, just one of them, and my vision for future work. So I see myself as doing math plus X. That is to say, in my case, the math is combinatorics, linear algebra, and graph theory. In my case, the X here it's a rank 2 vector here. It's high-performance combinatorial scientific computing. And it's also, X is not just the algorithms and the theory, but the applications that are enabled by my work. I'll give you then a roadmap of my past, current, and future work in terms of sort of a performance scale of where I am, where I hope to be going. Then, what I'd like to do is to give you one short example that is actually someone else's work, but it's a nice, tight example of how sparse matrix algorithms lies in this beautiful interplay of graph theory and combinatorics and numerical linear algebra and how the two inform each other. I'll talk about some of my contributions to the field, from theory to algorithms and a lot of algorithms and reliable software to the applications. In particular, Sparse Cholesky and also the update downdate problem, a sparse LU and sparse QR. And as Professor Kennedy says, all three of these appear inside / when you do it, and many other places as well. I'll talk about my current work in highly concurrent methods on both either massively parallel GPU systems or massive CPU cores. And this is work supported by NVIDIA as an academic partner. And then I'll talk about some of my future vision of where I hope to be going in the next near term and future years. So as I said, math plus X for me is high-performance computing and applications. But it's not just, it's high-performance combinatorial scientific computing. Combinatorial scientific computing lies at the intersection of two kinds of mathematics, combinatorics and graph theory, problems to solve, heuristics for solving NP-hard problems. And on the other side, on the right here, is linear algebra, finding least squares solutions, matrix partitions, and iterative solvers, and direct methods, and all of the numerics that go behind these methods. They come together here in combinatorial scientific computing, but they don't exist in isolation. They rest upon, if you will, and they drive applications. Okay, and all of these different applications are, in fact, users of my software. So I'll talk about MATLAB, NVIDIA, Google, for example. Whenever you pull up Google Street View and look at a photo on Google Street View, it's been placed there with a nonlinear least squares solver that calls a linear least squares solver on a matrix that happens to be mostly sparse, and so they use my solvers to do that. Mentor Graphics, a lot of the circuit simulation companies and finite element packages use these solvers as well. So as a roadmap, this is a broad brush view of some of my work and some of the performance metrics of it. It's color coded. First of all, simplicial methods. By those I mean methods that don't use dense matrix kernels. They get rather modest performance in terms of gigaflops, but in terms of the algorithms that they enable, these are actually very good kinds of methods to use for some problems, in particular circuit simulation. So I wrote a sparse solver specifically targeted for circuit simulation problems, which is up to 100 to even 1,000 times faster than the solver used in SPICE. And it's been in use in commercial circuit simulation solver packages that come out of companies here in the Bay Area. Moving on, I've developed single core methods that use multifrontal and supernodal methods to enable about several gigaflops in Sparse LU, QR, and Cholesky. All of these appear in MATLAB. These methods also extend to using multi-core shared memory systems, BLAS-based, and also parallelism across what's called the elimination tree. These can get upwards of 10 to 15 gigaflops on a modern typical desktop type or server rack multi-core shared memory machine. There's some chairs in the far back there. These can reach this sort of performance in backslash and other of my solvers on large problems, particularly 2D and 3D discretizations. And in red is what's happening in my work right now of GPU algorithms. And on a single GPU, this, in fact, nobody touched the screen there. It might get a little wet. The ink isn't dry. This is a result from Friday. This 80 gigaflops we got in a sparse multifrontal QR factorization end-to-end, doing the numerical factorization on the GPU, and it's up to a 9x speed up over the same algorithm running on, or a very high performance algorithm running on a multi-core CPU. In the future, though, to do LU and Cholesky, I'm going to need new algorithms and new GPU kernels as well to do that. This is sort of like the groundstone of what I'm, or the touchstone of what I'm trying to go for into the future, which is to, now that I can do a sparse QR on a GPU, I can then very easily chop this problem into pieces and use different GPUs or different multi-core systems in a single shared memory cluster and hope to get up to close to the teraflop performance. And this is I think, feasible. Going further to thousands, tens of thousands of cores needs a distributed memory system. And given that it looks like we can do this, we should be able to move ahead to distributed memory algorithms for very, very large matrix problems. All of this towards the goal, really the dream, I should say, really, to be fair, of exascale computing. I don't know if I'm going to reach that far, but it's something to shoot for. So I'd like to next, before I dive into the details, discuss with you, show you some of the places, some of the where these solvers are in use that have basically become part of the infrastructure of scientific computing. I mentioned Google, so every time backslash solves a sparse matrix, it uses my solvers, except for a sparse symmetric indefinite solver, which is by my postdoc advisor, Ian Duff. Mathematica, NVIDIA uses my solvers, Octave, R, Julia, many different packages in general scientific computing. It appears in all the Linux distros, the major distros. It appears as the sparse solver, as the direct sparse solver. Okay, all these packages often have other methods to solve very, very large problems, iterative solvers in particular. But it's often these packages that have multiple solvers they can switch back and forth between depending on the problem. But all these finite element solvers use them. Some of these are commercial. It's used, as I mentioned, very heavily in circuits and power and semiconductor simulation. And this really I should break it up into two categories, because there's two kinds of circuit simulation. There's the SPICE-like circuit simulation that, if you're an electrical engineer, you know what that is, of resistors and transistors and capacitors. You end up with a differential algebraic equation. You end up with a matrix that's very, very sparse. And so I did work with Sandia National Laboratory. They have a solver called Zeiss for doing this. They want to know if you push a button on your nuclear weapon, will it go off? And they want to do that without pushing it, right? It's computational. It's better to blow up a nuclear bomb computationally. It adds a new twist to the idea of when your code crashes, though, doesn't it? Core dump, radioactive core dump. So they use my solvers in that package. But some of these others, like Cadence, for example, and Mentor Graphics, use my other solvers that exploit dense matrix kernels on things like VLSI design and extraction, where it's really a partial differential equation across a discretized domain. So it's a very different kind of structure. And then finally, computer graphics and computer vision, robotics. I mentioned Google. So Google Street View sets up a nonlinear least squares problem to place photos. And you want to drive down the street and you want to see a photo in the right place. Well, the Google streetcar, the car that drives and takes these photos, has GPS coordinates for these photos. But if they were just to put those photos in place, they wouldn't be in the right place. It'd be a mess. You'd stand in a street corner and you'd see a field instead of there's supposed to be a building there. What's wrong? And you wouldn't use it. So they have to get these photos to agree. It's called the sparse bundle adjustment problem, nonlinear least squares problem, for which inside they need to solve a linear least squares problem on a large matrix, and that's where they use my solvers. And they've supported my work to do that. The U.S. Geological Survey uses my solvers for the same kind of problem, but it's on Mars and Mercury. They're building maps of Mars and Mercury. The Open Slam is a website that is dedicated to robotics projects. People post their robotics packages there. And all of this methods there where you've got that need to solve a similar kind of problem, simultaneous localization and mapping problem. You want to have a robot driving around, taking photos, building a 3D map of what it's seeing. You need to solve a least squares problem, and you need a sparse solver. So all of the packages there that use sparse matrix computations use my solvers. So I've been very blessed to be able to make these kinds of contributions and to get my students to do the same thing as well. You recognize some things up there, maybe another one. Mathematical optimization uses several of my solvers, and I've also contributed to mathematical optimization with a solver with a colleague of mine in the math department, Bill Hager, at the University of Florida. And I've also done some work with lots of other faculty. Les Foster is here. I've worked on some sparse QR rank detection with him, and very happy to have him here today. The geophysical modeling, earthquake simulation. So when the big one hits, you can blame me, maybe, if my code gets it wrong. Financial simulation, so the next financial crisis, blame me for that too. I better leave town. This is not good. Not good. Lots of different kinds of applications. This just gives you a snapshot. It's really just those applications that have nice logos. So if you want your project on a screen like this, you've got to get a good logo. I don't have a logo, so I could use some artists to give me a good logo. Oh, well, maybe this one will work. These are also more applications. This is from an article by fastcompany.com that did an article on these matrix visualizations and entitled Geeky Science Problem Double as Works of Art. And they called me a math nerd in the article, which, yeah, I like that. So sparse matrices are a lot prettier than they sound. This is just one matrix from my collection. Some people collect baseball cards, you know. I collect matrices. Matrices that come from real applications. Matrices that stress my solvers. Matrices that test my solvers. The reason I do this is that it's not good enough. These matrices have structure. They have properties. And it's not good enough, at least for a sparse direct solver, to use, say, an Erdős-Rényi graph let's generate a random matrix and plunk some entries down. You don't get good properties there. In particular, with very modest assumptions, it's been proven, I should add, that an Erdős-Rényi graph with order n edges takes order n cubed time to factorize. So it's really a dense matrix in disguise. It just happens to start out very sparse. So you have to have problems with real structure. This is a force-directed graph visualization of one of the optimization problems in my collection. And you can see, of course, it's very structured, but not perfect. It doesn't have sort of perfectly characterized structure, but there's some kind of structure to this problem. About a third of these matrices I collected myself from my own users of my own software. So generates a lot of ways to break my code, which is a good thing. You want to break your code and see where it fails. Okay. So next, I'd like to show you this algorithm, solving a sparse lower triangular system. Okay. This is where L, X, and B are all sparse. And this will show you the interplay between numerical linear algebra and graph algorithms. And so we want to solve a lower triangular system, and we want to do it optimally. Now, the non-optimal time for this, though, this algorithm, we just walk down column by column and subtract the jth component of the solution from the right-hand side. And this step right here is easy to do. the innermost loop, can be done in order flop count. There's a problem with this algorithm, though, in that, well, you can certainly see that if xj is 0, you can skip the entire computation. And so I'll just add this test here and skip the work. That'll speed the thing up. But you get this little order n here, which seems rather innocuous. Okay, where this is the number of non-zeros in B, and this is the flop count. But this is a problem. It's a problem because the matrix is, say, million by million. The flop count could be a constant. So we're talking about an algorithm which should be able to do constant number of flops. It's taking a million or order n flops, and it would just be way too slow. The solution then is to say, well, suppose we know the answer before we get it. That doesn't help much. But more precisely, we know where the answer is non-zero. And if we could just iterate across the non-zeros where it will become non-zero, well, we don't have it yet, then we would know the answer. We could just iterate across that list and get the optimal time. How do we do that? Well, the answer is a reach in a graph. It's a purely combinatorial result, and it's shown here. So the idea is to ask the question, well, where does this thing become non-zero? It becomes non-zero here when x is assigned to b, or b is assigned to x. And x becomes non-zero here. And here the rule is, well, if there's an xj that's non-zero and an lij that's non-zero, then that makes xi non-zero. And I'm cheating a little bit because, well, maybe it drops to 0 after the fact. 3 minus 3 to me is non-zero. It's shorthand. It's something we actually compute. I'm using the term non-zero for an entry that's of interest. So put quotes around that, if you will. But this is the first rule. So what we can do is to solve this problem is to create a graph and just simply follow these rules. The rules start here. If xi is non-zero, if b sub I is non-zero, then x sub I is non-zero. Then we have to follow these rules to see how they trigger. We go from xj, we create a graph with an edge from xj to xi whenever lij is non-zero. That's just the graph of L itself. So there's nothing to create. We just have to follow that graph. And then the solution then is put your fingers on the nodes of the graph corresponding to non-zeros on the right-hand side and ask, where can you go? You can't get there from here, but you can get here. All the nodes you can reach then in the graph starting from these nodes is the non-zero pattern of the solution. So you get this beautiful tight combinatorial result. X is the reach in L of B, and that describes the algorithm and what needs to be computed. And the cool thing is that this graph traversal, is proportional to the number of edges traversed. Each edge corresponds to one of these rules. Each rule corresponds to one firing of 2 flops in this statement. So order edges is order flops. So we have the perfect time. Here's an example. If B4 and B6 are non-zero, from 4 we can reach 9, 12, 13, and 14. From 6 we can get to 10 and 11 and so forth. And all these red entries take part in the work. And there's the answer, the non-zero pattern of the solution. You notice that it doesn't look sorted, but it is. It's topologically sorted. That is to say, all the edges in this list go from left to right. And that's sufficient. Sorting it, for sure, sorting it in a strict order would add an extra logarithmic time, which we don't want to spend. So that, I hope, gives you a picture of how the numerics and the symbolics couple together. And what I'd like to do now is to show you a few specific examples. The Cholesky update downdate problem, which will rely on that result. The Cholesky update downdate problem arises in several places. But the idea is you're given a factorization, you've already computed it, and it undergoes a low rank change. So, oops, that's not, you factor a matrix and you go, I could have factored the other matrix. I want to solve a different problem, a slightly different problem. I want to patch up or update the factorization to solve this new problem. This arises in many places: optimization, crack propagation, airline fuselages. I did some collaboration with a guy on that, and as I was writing my notes on the way over here, looking at the airplane I'm flying in, I'm thinking, I hope I don't have to solve this problem in flight. Robotics, as new data arrives, I've got a robotics collaborator who's using this update downdate. A new image arrives, and we don't want to recompute our 3D map from the beginning. We can update it using the update of the Cholesky factorization. Well, they say that if you put equations in a slide in a talk, every equation cuts the audience in half. So you've just been reduced by about 2 to the minus 12. asymptotically 0 now. Nobody's left. This is a rank 1 update. This is the numerical work. Okay, I don't expect to go through, you look at every equation, but the gist is this. Okay, this walks through the matrix and patches up the columns to give you the factorization of the new matrix. But the key observation, and this is what I do with a lot of algorithms, you look at the algorithm and say, what is it computing and how, and what are the numerical dependencies? And look at the red lines. Alpha is Wj over Ljj. That's like dividing a triangular system by the diagonal. Ooh. And then that's the same thing. And then take that and subtract it off the right-hand side. Well, we just saw that. This is doing a triangular solve right in the middle of this algorithm. So W is being replaced with L inverse W. Oh, then what's the non-zero pattern W? That's important. We know that. We know what the answer is. And then, then you can observe, if you walk through these coefficients, you realize, well, wait, if Wj is 0, I can skip all this work. So we have the solution. We know where the entries change. The cool thing is that Cholesky factorization can be pruned, and you end up with something that was actually created by Rob Schreiber, I think. Didn't the elimination tree came from him. He's here in the audience. Nice to have you here. The elimination tree. This graph of L the matrix L has a very rich set of properties. With the rank 1 update, okay, if L, let's suppose for the moment that the graph of the matrix doesn't change. We can change it as well, and we can change the tree dynamically and figure out where to change it and make the change. We've got that in our algorithms. If the matrix doesn't change, then the columns in L that change are exactly a single path starting from the smallest entry that's non-zero in W to the root of the tree. So this graph traversal of putting your fingers down and seeing where you can go, it turns into a single path. Take the smallest the smallest row index of the non-zero pattern of W, your incoming vector, take that node, say it's 3, walk up this tree, which has already been constructed. The tree is such that the parent of a node is the first off-diagonal non-zero in the column of L. So the parent of 3, for example, is 8, which is this entry here. Okay, the parent of 3 is 8. Now, suppose the graph does change. We handle that case. The tree changes. And then it turns out that we just simply have to follow the path in the modified tree. The cool thing is that after all of this symbolic analysis and figuring out the combinatorics of where things change and how, we end up with an optimal algorithm, asymptotically optimal algorithm. We can do the update, downdate in time proportional to the number of entries in the matrix graph that change, which you can't do any better, at least within a constant. We extended this to the multiple rank problem. When lots of things coming into change, you have a W of rank 2. And what if the first entry in one is 3, and the second column, the first non-zero entry, is a 7? Then you end up with 2 rank 1 updates that follow the tree. But what happens when they collide? Ooh, we can exploit that. Then we can do a rank 2 update on the node at which they collide and then walk up. So we exploit that to get yet higher performance and better memory cache behavior. I should add, by the way, that I'll mention as the talk goes along things about cache this and memory traffic this, and isn't that just an engineering concern? No, it's not. It's actually a deeply theoretical, philosophical, physical concern. Okay, I'd like to tell my students there's no such thing as RAM. RAM is non-existent. Order 1 time to reach memory of arbitrary size, that doesn't make sense. We live in a 3D geometry and 1D of time. If I want memory that's this big, I can, in 1 nanosecond, go 1 foot and get it and bring it back. If I have bigger memory, I have to go farther to get it. So the bigger the memory is, right, the axis of time of memory has to be at least order to n to the cube root. That's if you stack memory in 3 dimensions. So dealing with cache is important because you're dealing with fundamental theoretical physics. Okay, so in a multiple rank update, we follow multiple paths. We can modify what are called supernodes. A supernode is when columns of L have the same non-zero pattern. So here, for example, supernodes, there's not too many of them. 9, 10, and 11 is a little dense rectangular matrix. What will often happen in a Cholesky factorization, you have adjacent columns of L with the same non-zero pattern except for the diagonal. And we can store those as a little dense submatrix and then operate on them. They sometimes not very little. They can be quite huge. Operate on them inside using regular memory traffic, regular memory operations, dense matrix operations, which exploit cache better. And why do we care about cache? Because it's deeply theoretical. It's not just engineering. I'm an engineer too, so I like that as well. It wouldn't be bad if it was just engineering, but it's also theoretical. Okay. Another thing that's really cool is we can merge and break apart these supernodes as the pattern changes. Things become the same, and then they become different. We do all that. Okay. The LP-DAS, or linear perturbing dual active set algorithm, is an optimization solver that needs to maintain the Cholesky factorization of a basis matrix. And as the basis changes, columns come and go, it leads to a low rank change. And then you need an optimal algorithm inside to do that. The other thing is this robotics example I gave, building a map, updating and downdating, and the crack propagation. You hope the plane doesn't fall apart in midair. But it does that. The crack will slowly propagate, and as it gets pressurized and depressurized, and you don't want you want to model that, obviously, to figure out when it's going to occur, and then the problem changes only just a little bit. You have this large structure, and the crack progresses in a way that you figure out where it progresses, and it needs to progress. So your graph, your matrix changes just a little bit. It's a low rank change. You don't have to factorize the matrix all over again. It leads to a great speed up in the analysis of this. So some key results and impact of this work. It's the Sparse Cholesky in MATLAB in \. When it was incorporated into MATLAB, I got about a 10x speed up over the previous method, which was not using supernodal techniques, the dense matrix kernels. The peak performance is very exciting. It's up to 50% of the bare metal performance on a single core CPU. It's a little bit less on a multi-core machine. And I gave you some examples here, Google Street View, but also Mentor Graphics for circuit simulation, CAD design, convex optimization. Lots of different places are using this solver. The other solver I've done is an unsymmetric multifrontal method. And the multifrontal method organizes the factorization very differently. And this is going to be a segue into my current work as well. The classic method, and classic, it's not 1,000 years old, it's 30 years old, by Duff and Reed and others, takes a matrix, assumes that the non-zero pattern of this matrix is symmetric. And what it does is it exploits the cliques that arise during the numerical factorization. Okay, so think of a graph. Y'all thinking about a graph? Now, grab a node of this graph. That's your pivot row and column. What's the adjacency of that graph? Well, in the matrix, it's your pivot row and it's your pivot column. Now, do one step of Gaussian elimination. I guess I should, unless you're dyslexic, maybe I should do it that way. Okay. Do one step of Gaussian elimination and annihilate these entries. What do? You touch the matrix here. What is this? In the adjacency matrix, that's a clique. So taking this graph, grabbing a node, making a clique of its neighbors, and then cutting off this node and throwing it away is the same thing as one step of Gaussian elimination. So we're adding cliques. We're not finding cliques. We're adding cliques to this graph. This graph is changing dynamically. These cliques are important because a clique in an adjacency matrix is a dense submatrix. Dense submatrices are great because dense matrices are great. Even though I do sparse, I do all of my flops inside dense. Okay? And so here, for example, is a clique of nodes 4, 6, and 10. You do one step, say, of LU factorization, and you stop here. You're left with this red component, which is the Schur complement. And you can't factor this because you don't have all of row 6, just part of it. You have all of row 4 and column 4, but you don't have this. So then you take these terms and add them here to the green in the parent. So one clique consumes the other. Parents eat their children in this example here. So all of the work is done inside these dense matrices. The dense frontal matrices, they're called, and it's governed by this elimination tree. Who is your parent? It's your first off-diagonal non-zero. 7, the parent of 7 is 9, for example. Okay, what I did, so that was work by my postdoc advisor, Ian Duff, and others, but he was the one who really did a lot of work in this area and continues to do a lot of work in this area. The thing that I did about now 20 years ago, which then 15 years ago became sparse LU in MATLAB and in backslash, is UNFPAC, which is the unsymmetric multifrontal method. And I did what mathematicians in computer science do all the time. If you got a problem and you have a bunch of assumptions, you say, well, oh, what if I take out this assumption? Let's take out the assumption that the pattern is symmetric. So this example, what if I say, well, hey, I've got a pivot row and a pivot column, and they're different. You get a bipartite clique in the bipartite graph. And the frontal matrices become rectangular, like this. The other thing that's really cool about this, it makes it more challenging actually, is that you have these frontal matrices. I have an upper bound on how big the frontal matrix can get, but because of pivoting, I don't know how big they could get. The upper bound is the same as a QR factorization. But what happens is the data just doesn't go into the parent. It goes into an ancestor in the tree. So this data here, this entry, once I compute it, has to go to this parent. But the other column here in entry row 7, column 7, has to go all the way up to the grandparent. And if I made the parent big enough to take everything, then it would take up too much space, too much memory, and too much computation. So that's the unsymmetric multifrontal method. And some of the impacts, I get, again, high performance via dense matrix kernels within each front. It's preceded by symbolic pre-ordering and analysis. And then I can revise the local pivot search. What's really cool about this algorithm, it uses an unsymmetric variant of something called the approximate minimum degree, which I won't have time to talk about, but it's basically a way of, so what am I doing? I'm going to talk about it. Taking this graph and finding these nodes and cliques, the order in which you do it, you can do it by order of degree. Pick the next node of least degree. Okay? But now updating the degree is costly because we don't have the graph anymore. We have it as a collection of cliques. And finding the degree is to find a set union of cliques. So that's costly. So I found an approximation to that, an upper bound, which still gives a good ordering. I actually did that algorithm first in the unsymmetric context. And I maintain a right-looking outer product formulation of the matrix. And so I could extend this method to handle threshold rook pivoting and all kinds of other possible interesting algorithms. It's widely used. It's used in finite element solvers, Mathematica, and MATLAB. Okay, so then on to my QR factorization. It's very similar in many ways to the unsymmetric LU factorization, except now those upper bounds are actually reached. All those little boxes with some empty dots, and they're all got lots of dots. The numerical assembly is also different. It's now a concatenation. So what happens in QR factorization, imagine if I had, say, here, suppose I've got two matrices, they're tall and thin, and I factor them, okay? When I factor them, I'm left with two triangular factors. I guess I should use diamonds instead. Okay, when these two children go up to the parent to be factorized, I factor them all the way to the bottom, okay? But what's left over in these two submatrices is part of the final R matrix, but some of those rows that have been factorized aren't done yet. They need to be concatenated together like this, not added, and then do another QR factorization of the resulting algorithm. So there's a concatenation that happens instead of the summation that happens in LU and Cholesky. That makes it better for massive parallelism because concatenating data is easy. I can have one process go splat and another thread goes splat, and they don't have to talk to each other. But if I have to add, okay, it's less parallel. You have to have an owner compute rule or have synchronization. So we're targeting now a GPU implementation of this algorithm, which, as I said, we just got working Friday, just in time for this talk. And here's some of the current algorithms current performance of this algorithm. This is a very large least squares problem, 2 million by 110,000. I believe this problem comes from the European Space Operations Center. They've got a lot of particles and debris floating around the Earth, and they want to find the orbital parameters to figure out where these pieces of junk are flying. The previous backslash in MATLAB, I actually let it running for like 2 weeks and finally killed MATLAB. Okay, if I used a different ordering, I actually did get the solution in x equals a backslash b hit return and come back the next day in 11 days. Using a better algorithm by Ian Duff, cut it to 3.5 hours, a multifrontal algorithm. Using my version of the multifrontal algorithm, cut it time another factor of 2. Using a better ordering, cut it a factor of 2. Using parallelism, cut it down to a factor of 6. and the total speed up is 2,000 over the previous method. Okay, less over a good multifrontal previous method, from 3.5 hours to 7 minutes. And the other thing about this algorithm, it gets 2.5 gigaflops peak, the same as LAPACK on a dense matrix. This is what my GPU performance is going to be compared against. So when I say the next algorithm is X faster than this one, than sparse QR, it's comparing against a very, very good one. I mean, I'm sure this could be beaten, but it's getting some decent performance here. So highly concurrent heterogeneous computing. I believe that the future is heterogeneous because GPUs and CPUs can solve different problems in different ways. GPUs are very simple cores. They're very power efficient. They don't handle superscalar instructions, however, but you can have lots of them on the GPU core. A GPU breaks up into multiple streaming multiprocessors. They're called SMs. On the GPU, on the Fermi, you've got a single chip with 14 of these, each of which has 32 computing cores. The computing cores inside each M work in lockstep, in warps. And so they're very easy to synchronize with each other. Between SMs, they don't like to synchronize with each other. They can. They communicate via global memory. They do have ways of coordinating with each other. But the best way to program these things is the bulk synchronous programming model, where you just basically tell, here's a bunch of parallel tasks to do, and go do it and then end of a kernel launch is what I'm going to use in the later phrase, a kernel launch. And then at that point, we can all see the data that we all produced. Each task, though, is itself a parallel piece of work. Within each SM, all these threads are working in tight lockstep fashion. So tight synchronization built in inside the SM, one SM, and then barely no synchronization between the SMs. Okay, so that's how GPUs work. And what we're going to do here that's very different than what's been done before, people have tried GPU computing before. They'll take one of these matrices, okay, send it off to the GPU, bring it back, do the assembly on the CPU, create another front, basically using the GPU as almost like just a BLAS accelerator. Okay, I don't want to sound like I'm too deprecating of previous methods. But that's how previous methods work. What we're going to do is different. I'm going to take the whole deck of cards, all the fronts that I can, and put them all on the GPU and let them all go factoring at the same time. Now, there are some dependencies between the frontal matrices from the elimination tree, but the CPU knows that, and the CPU can tell the GPU, some of the tasks are, okay, you, SM, you take your contribution block from your matrix, and you add it to the parent, and the data stays on the GPU. It does not come off the GPU, because the CPU-GPU communication is fairly slow compared to the bandwidth of memory on the GPU itself. So I'm going to show you an example, and again, I'm going to use my little toys here, my cards, of a scheduling algorithm that we run on the GPU. It's an extension of something called the communication avoiding QR by Demel and Grigori and others. And the idea is this. We break our dense matrix now, because we're inside a single frontal matrix. I've got lots of these going on, a whole deck of them, okay, but this is just focusing on one of them. Now each card is going to be one of these tiles, actually a row tile. So I'm going to have 8 cards in my hand. 4, 5, 6, 7, 8. Okay, so I have 8 cards, and I have 5 buckets where these cards can reside. And they're going to start out, a card is going to stay, I'll have 6 cards in bucket 1 and 2 cards in bucket 2. So there's bucket 2 and there's bucket 6. Okay. So the scheduler is maintaining these buckets. And here's the first task. What we want to do is, within an SM, we have a lot of very good high-speed sort of lockstep synchronous parallelism. But the SM has a very small amount of what's called shared memory that the SM can access. All the threads can work on. It's very tiny. In this case, it can only hold a handful of these 32 by 32 matrices. So my hand can only hold 3 cards. That's 3 tiles. So I'll tell the GPU, okay, one SM, here's one task. Take these 3 and factorize them, leading in that upper triangular little black triangle. And then another SM can do this. And another SM can go to any bucket that has 2 cards or more, I can pick up and create a task. So I have 3 tasks created. Now this is already slightly different than than the communication avoiding QR because I'm looking ahead to subsequent columns. Well, this is kind of a vanilla exploitation of that idea. And the next step gets really colorful. Now, you notice here on this first step, all these tiles are idle, gray. Gray is not good because the matrix is sitting there and it's like, somebody factor me, please. It's not getting work done. We want to get work done. We want to see color splat all over the place. Well, there we have it. It's very colorful. No gray. So what's happening here is several things. Okay, we could, after we factorize this purple, okay, we could then apply the factorization. We have to apply the factorization in the next step. So think of factorizing this. You get a block householder, basically a matrix Q, which is stored in a convenient way on the GPU. It then needs to be multiplied here on the next kernel launch. So what you'll see on the next slide is purple swathed across here, and you'll see red and you'll see green, but you'll see more because we can start new tasks, new factorization tasks. So there you see the red apply from the previous. I call this a bundle. It's a set of, I really should call it a hand maybe. So I have the red one and the purple one and the green one being applied. That's the multiplication by Q. And that can be done in parallel or they can be congregated if need be. But something else can happen, which I call pipelining in this context. The idea is this. Why, if I did the following, if I picked up these cards, okay, you need to factor it, and put one goes back in the bucket it came from. That's the upper triangular factor. The other two move on to the next bucket. Okay, put them down, and then come back later. Oh, and now do the apply for this, for the next kernel launch. Well, wait. Think about what happened in that yellow space there. We had an SM, okay, who can pick up the factorization computer on the previous kernel launch. That does need to be done. But on the second kernel launch, there's an SM that has to take this factorization and apply it to column 2, the one that's partly yellow. Well, I could apply it to column 2 and then put it back. Well, wait a minute. I just had it in my hand. Why don't I factor it right now? That's the yellow, and it's replaced with an upper triangular factor. So this thing goes to 0. I should use a stick and not speak softly. Okay. All right. The next thing is I call bundle growth. And you need all these features to get the algorithm to go fast. In bundle growth, we have the purple bundle was tiles 4, 5, and 6. 4 is discarded. Okay. But then when we go to apply this bundle to this tile column, we see in bucket 2, hey, there's somebody sitting here. You're just sitting there idle. This is the R factor that came out of the green factorization. This green factorization is being applied here on this kernel launch, but this is just sitting here otherwise idle. But I need to zero it out at some point. Why not? Like, I can hold 3 cards in my hand. I did a discard. You didn't know you were playing card games today. Discard and take a new card. You do this all the time in playing cards. Why not in GPU computing? Okay. So that's the blue. There's another thing that can happen. There were 2 discards from these previous launches back into the column bucket 1. These 2 light blue R factors. Okay, I can start another kernel launch for these 2 to factor them because in the end I want just one upper triangular factor here and here. My goal is to make it upper triangular. Okay, and that's what the next step does. And you don't like gray tiles. Bad tile. Okay, those are not good, but there's very few of them. So the yellow gets applied, the light blue gets applied, the dark blue is applied, the blue can pipeline and grow. Yellow is really cool. What's happening to yellow? Yellow is just tiles 2 and 3. It discarded tile 2, and it picked up 2 new tiles, 4 and 5. They don't have to be contiguous. Why not? Do a little householder factorization on that, what it turns out to be a 96 by 32 matrix, factor it, next step, we'll apply it, and so forth. I'm not going to show the rest, but here's an example. The color now, gray is an idle tile, yellow is a tile that's being applied to or factorized. Green is a pipelined case where I've got I'm reusing this space to do a pipeline factorize. Blue is a fresh bundle picked up from scratch. Okay, so this is the full-blown algorithm. This is 4 different factorizations of slowly hobbling the algorithm. This is the real algorithm here. But if I take out the bundle growth, your hands in your card get smaller and smaller and smaller. I mean, if you start out with 8 cards in your hand, if you can hold that many on the GPU, okay, because they factorize. You know, it gets smaller and smaller and smaller and smaller and smaller, less and less and less effective. Okay? And you end up doing more flops. So this is not good. And it's not progressed as far either. Now, this looks very irregular. Okay? It's a deterministic schedule. It is not random. It starts with no staircase. There's nothing in the beginning that makes it. It's just picking up cards off the table and factorizing it. What you see here is the parallelism. What you see here is the number. You see the kernel launches from 1 to 85. The red is the best algorithm. It finishes in half the time as these other methods. And this is the number of parallel tasks in each launch. Now, blue looks great. Blue is this one. It's not great. It's doing more parallel tasks, but they're less effective. It's doing more flops for the same problem. Okay? This one right here is with no pipeline and no look ahead. You just sit and work and work and work and work until this column becomes upper triangular. Okay, so it's like a quaternary tree. It's a 4-way tree of factorizations that finally lead to a single tile here, and then it applies it to the right as you go. But that's the slowest. And what's happening? It's jagged. A lot of work, a little work, a lot of work, a little work, because factor and then apply. Factor is very sequential. Apply is very parallel. And the other one is the flops in each step, and you see the blue is higher as well. So let me give you a little dynamic picture here. So this is the full pipelining algorithm. This started out as a dense matrix with no structure to it, but you get this very interesting combinatoric sort of thing. This is pipelining with no bundle growth. You see, because there's no bundle growth, you see a lot of fresh tiles that are in blue that get picked up because all this detritus gets left behind. You have this. You're constantly, discard, 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 discard. Well, somebody coming up behind you and saying, "Oh, I can factor that. Oh, I can factor that," and it generates a lot of very small bundles. The last one, you notice there's a lot of gray tiles. Not a good thing. You could have been doing work, and you're just slacking off, like me in graduate school. Get to work.
The launches are kernel launches? Or
yes, each is a kernel launch.
And is there a way to avoid all these kernel launches? Is there an impact?
Is there, I'm sorry?
Is there an impact of all these kernel launches? I mean, could you get away with fewer launches?
Well, let's see. Well, we have almost an optimal algorithm here with the full pipelining, in terms of the kernel, the way the problem is structured. Because on any given kernel launch, it's very difficult to synchronize between the SMs in a GPU. You can, but it's slow. So you don't want to have one SM touch a part of the matrix and have another SM and come and touch the same matrix, because you don't want to have numerical dependencies between that. Okay? So you'd like to just touch every part of the matrix. Touch it. We only touch it once, but then if you touch it at most once, you want to touch it at least once, so you keep the matrix busy. What that means is you don't want any gray tiles. So during this factorization, you want to see work that's no gray tiles, and you see a few here and there. So it's mostly busy.
My question is, I mean, there is probably a way to, not sure, but it feels that there should be a way to have, for example, only one kernel that constantly generates and consumes work.
Oh, on its own, you mean?
Right. So that you have to relaunch.
Okay. Okay. No, it's not a problem. What the way the GPU works is it's designed that way. Okay, and you may worry about, the GPU is sitting there idle while I'm playing with cards. Come on, get to work. Well, this schedule is deterministic, and it's double buffered. So what happens is the CPU creates the launch, creates the set of tasks in the kernel launch, It tells the GPU all the things it needs to do. It sends that to that just bunch of integers. It's no floating point work because that's already on the GPU. We've shipped that asynchronously already. By asynchronous, I mean you start the transfer off and you go off. The CPU is free to go off and do other things. The CPU creates the schedule and sends it off to the GPU. The GPU now is working, on all these factorizations. While the GPU is working on this kernel launch, this set of parallel tasks, the CPU is playing card games here to say, oh, well, I can do this. And it's building the next schedule for the next kernel launch. So it's one step ahead. So the time it takes to do the scheduling is itself negligible. It's washed away. And the GPU is designed to do this bulk synchronous computing where you give it a bunch of parallel tasks and say, go do it all in parallel with no dependencies. Check. Go do a whole bunch of stuff in parallel with no synchronization, no dependencies. Check. Repeat. That's one kernel launch. The GPU is designed to do that. So it's very fast. And then this GPU schedules all these parallel tasks. So that's the way it's done and how we get our performance. So the bottom line, of course, is in the performance. How good is it? Whoops. MATLAB is not changing slides for me. Oh, MATLAB can do a lot of things. It can't change your slides. Okay. Here's the performance we're getting on Fermi. Fermi has 448 cores split up into 13. That's a very odd number. I'm an applied mathematician, and even to me, 13 is odd. Each has 32 cores, so it's got 448 processors. The theoretical peak of Fermi is about 500, but the practical peak, because it's not a superscalar machine, when you load a register from a value from register or from shared memory to register, it takes one clock cycle to do that, and it's a flop when you load a register. It costs you a flop. So in practice, the practical peak is about 300, and our block apply is running at 183. And the factorization is only running at 27, but it's done much less of the work is done here. We can do a dense QR of a large front at about 100 gigaflops on one GPU card and about 120 on a different machine with the 2,000 GPU cores. And this is exciting. We're getting our sparse QR to run at 80 gigaflops. This is the one that runs about 14 or 15 on a multi-core CPU. Okay? And on some problems, we're seeing a speed up over the CPU of a factor of 9 times faster in the factorization than on the CPU. And the CPU is already running a very good sparse QR, multifrontal QR. Now, I should also add that this 80 is actually conservative. I'm not lying with this 80 in the sense that there is some extra work. I mean, it would do less flops if we didn't use block householder operations, which I haven't defined. But the idea is that you could just eliminate the matrix one column at a time. Take one column, apply it. One column, not a column tile, but a single column. You get the fewest possible flops when you do that. But it's not very parallel. It's better to group the stuff together. It's better to do sub matrices, and you factor this, I'll factor this, and later we'll join and factor what's left. So I'm doing a little bit a few more flops, about 40% more. So the actual work that the GPU is doing, if you counted that as the gigaflop, it will be 120. But if you're more conservative, you say, well, okay, you finished in X amount of time, and an algorithm which did the least number of flops possible would do X amount of flops, so X over this time is 80. Okay, so that's a more fair. But if you want to know how close you are to the bare metal performance, we're getting 120 out of a machine. We're about a factor of 3 away, which if you know anything about GPU computing, it's really hard to get that high. A factor of 3 away from a practical peak of 300. And Kepler, I mean, this is, as I said, this just is Friday. I'm on the phone with my graduate student, okay, it's not here yet, but we're close. Okay, this is, every dot is a matrix, okay, in my collection. And this is the flops intensity, the number of flops divided by the size of the problem in terms of the memory bytes of memory used. And the idea is this is a good metric for deciding how much reuse you can get in your problem. You bring in a word, you work on it. and you put it back. You bring in a word, you work on it. How many times you work on it? That ratio, the higher that is, the more effective a dense matrix kernel, the more effective a GPU is going to be. And you can see that after it gets about a factor of 100, the GPU is always faster. Over here is the CPU time with a good algorithm divided by the computing the same factorization but exploiting the GPU. And this is with the Fermi GPU. And this is 1 and 10 up above. And we're seeing close to a factor of 10 for very large problems. And that's where you really care about performance anyway. And there are no dots down in this corner. All right. You did not see this. Well, you didn't see this because, and I do this inside backslash. I do the symbolic analysis in backslash when I'm doing the Sparse Cholesky. I have 2 Sparse Cholesky factorizations in MATLAB, actually, not just 1. And I pick and choose based upon the matrix. I look at this flop intensity and I pick the one that I know is going to be faster. The same thing can be done here. Well, if you're under 10, then forget the GPU. If you're over 100, use the GPU. And if you're between 10 and 100, well, that's a research question. We have to work on that. Try to figure out what is a good metric. But so on big problems where the flop intensity is high, we get very nice results. So that's my current work. My future vision, and I'm really almost out of time, so let me go through this quickly, is, again, math plus X. Math in my case is the combinatorics, the linear algebra, and graph theory, and their tight interplay. I hope you've seen that. I caught a glimpse of how that works. X in my case is not unknown. It's known. It's high-performance computing plus the enabled applications. I believe that a lot of work in future computational mathematics is heterogeneous because we're pushing up against the edges of physics. And we need cores that are simple and power efficient. And when they're simple and power efficient, they don't have superscalar properties. They can't do prefetching and pipelining all themselves. You're exposed to the memory hierarchy. And the reason you're exposed to the memory hierarchy is because we can make it more efficient when we do it that way, more power efficient. And why is the memory hierarchy important? It's important because it's not just an engineering hack. It's important because we kind of live in a 3D world. And we're kind of driven by the fact that light only goes, this fast. I like to shoot for high impact solutions to hard problems. Novel algorithms. This is not just a matter of taking previous algorithms and porting them to the GPU. This algorithm, this scheduling algorithm here is brand new, cut from the cloth. It's also amenable, by the way. There's nothing that says that this has to be a GPU. This could be a multi-core CPU that's picking up cards. And you could have computational cores on the CPU that are doing the same work that's being assigned this parallel task. It's just an OpenMP for all, okay? There's a kernel launch. Do it all. If you have one CPU, one core that would do the scheduling, the rest that can do the, or a mix of the two, okay? I put a lot of my algorithms, and my students do as well, into published software. This is software that appears in the ACM transactions and mathematical software. It's rigorously tested. It's peer-reviewed software that is really important in my case because if you took, and I should have brought some reams of paper here, but if you took my sparse solvers in MATLAB and said, well, here's the algorithm, you go implement it, it would be a stack of paper this thick, and you wouldn't do it. So to deliver the algorithm, you have to deliver the software. And growing impact on different collaborators and growing impact on different applications. So I hope you've caught a glimpse of my passion and enthusiasm for scientific computing. Here's my roadmap again, but I'm running tight on time. You can see where I hope to be going. And in summary, then you've seen Math plus X, you've seen my roadmap. I've given you a description of how sparse matrix algorithms work, my previous contributions to the field, my current work in GPU or highly parallel computing supported by NVIDIA, my future vision, individual and collaborative, towards exascale, put quotes around this, and my goal then is to continue to create algorithms with deep impact. So that's my vision, that's my passion for computational mathematics. And another way that I like to, which I hope you've caught a glimpse of in this talk, another way I like to communicate my enthusiasm, my passion for numerical mathematics is math plus X, where X is poetry and art. And this is a poem I wrote a while back to express my enthusiasm for writing the code. So I took C fever and turned it into C fever. I must go code in both C and M, not only C and VI. And all I ask is a Linux box and a mouse to steer by. And the whiles break, and the if-then, and the Valgrind shaking, and a dash O, so the C's fast, and a switch case breaking. Thank you for your coming to my talk. Can I answer any further questions? Yes?
I have a quick question. In the earlier slide, you showed the tree, the diminished tree. You say that you can cache in the blocks, but if you do post-ordering of one of the matrix,
Yes.
no, not earlier, if you do post-ordering of the matrix, seems like you can creating a larger cache, right? Because
Yes.
but you don't do post-ordering.
We do post-ordering.
Oh, you do post-ordering.
Right. I just didn't go into that detail. And I drew, this is not a post-ordered tree. That's a very good observation, actually. Because when you go from 3 to 8, in fact...
Well, 8, 9, 10, 11, you can totally cache it.
Right.
So, I mean, sorry, if you exchange it at 7.
Yes, that's a very good observation. It's actually even more subtle than that, because as the graph changes, the post-ordering could change. Ooh, so we can't really do that. That's too much.
But when you're dynamically changing the modifications
Yes.
problem that you do, update, down.
Yes.
When you do update, you have additional notes.
Additional entries that appear. The matrix stays the same dimension. I can change that, but
Do you juggling the entries, or you just...
I make it bigger. Yeah, I make more. I put new entries in the matrix that weren't there before.
But then in the physical memory, do you attending in the back end, or you just dynamically extending the size of the submatrix?
I do it in time proportional to the number of entries that change. So I have a data structure for handling that dynamic growth. I keep the column contiguous, and if I need to, basically I put it in another chunk of memory. It's just a list.
So now you have the first ordering.
Yeah.
And then you never change the, do you change the increasing order of the ordering? That means that originally they are in certain sequence. When you're making an update or downdate, they might changing, optimally, you might changing the order.
The ordering can't change. If it does, if you change the permutation of the
permutation?
Yeah, then that's more, you're multiplying by matrix, that's not a low rank change. So even a swap would be, a swap might work. But much more than that, permutations can't be done. But one thing that can be done is a dynamic supernode. 3 and 8 are supernodal. 8 is the same pattern of 3 minus 3 itself. So they have the same non-zero pattern. That thing can happen dynamically as we go. And so it's actually kind of nice that they're different, because they can be different in the actual algorithm. And I exploit that. If I look at my parent and I say, parent, you are one less than me, I know parent is a superset of the children. If the parent is one less than me, I know that my parent is the same as me, and I don't need to look at my parent's pattern. I can just know that I know right where those entries are, and I don't have to look up the integers, and I can save myself a scatter-gather and treat it as if it's a supernode and get better cache reuse and throw memory traffic away. And it's all memory traffic is really critical. Yes?
On your map of the CPU, GPU time versus clock intensity,
Yes.
is there
The plot...
of the underlying applications? Can you say something about that, or is it somewhere between 1 and 10?
This one?
Yeah.
Unfortunately, I would love to. That's a great question. But I don't have that handy. I mean, where these applications come from. Okay, they come from all these kinds of problems all over the place. But I can't look at that and say which one. I mean, I know each one's a matrix. Whoops.
Yeah, but if you can connect them maybe to the underlying PDEs, the underlying optimization problem, so that...
That's quite possible, yeah.
Changing
Right.
that x-axis before you go to the
Right.
GPU implementation.
Right. What, I don't know if I have, well, I can't find it right now, but I have another plot I did for Cholesky with and without using dense supernodes. And this plot, on here, was, now I've erased it, was almost like a perfect shaped S-curve. It just kind of went like this, just a nice tight bundle. And so it actually makes it quite predictable. This is less predictable, and I've got to try to figure out, I mean, these are results, like I said, don't touch the ink, it'll smear on your fingers. It's literally just before I flew out here. So I need to understand why it's so noisy. Yes?
Related question, you're comparing CPU versus GPU time.
Yes.
The generic case is your GPU is attached to your CPU.
Right.
You want to use them both.
Yes. That's the blue on my roadmap, right? That's the near term. Right now we're just trying to, can we get the GPU to do the work? The multi-core CPU is just sitting idle. And yes, the next thing, of course, to do, which is then very easy, now we know we can get the GPU going fast. Now we can toss the CPU cores in, and they can be doing the computational work as well. They can be treated like another GPU. I mean, that's certainly on our horizon. That's the short term.
Well, there are some things that CPUs do better than GPUs and vice versa. So
yes.
Smart algorithm will divide the tasks.
Right. We'll consider that. But the CPU with dense matrix kernels, the BLAs, it can do these block applies, block householder factorizations. And yeah, we just have to crank the knob to figure out where that trade-off is, and input that into our scheduler to decide. Oh, here GPU, you do this chunk of work. Here's another subtree, you do this. And what are you? Oh, you're a multi-core CPU, you do this. And here's another GPU. Okay, here's another subtree, you do these fronts. And then the scheduler will be playing a multi-finger orchestra, if you will. Piano. This you schedule this, schedule this, schedule this, and then when they're all done, we'd have to pull this data off and combine them. But you're right. There's nothing to prevent us from using the CPU. So we're getting 80 gigaflops just on the GPU, basically. Let's see, Professor Moyne.
How do you handle round-off errors?
Round-off errors. Well, this is QR factorization, so it's householder based. So it's intrinsically numerically robust. If we extend this to LU or Cholesky, it's going to get dicier. And chopping up the work into independent pieces, we'll have to do this factorization just to find out what the good pivots are and then repeat. So it's not, and I might end up, I've talked with Laura Grigory, and she does work in this area. We might collaborate to try to figure out how to resolve that problem. But yeah, numerical accuracy is a big issue. But we're starting off a problem here with sparse QR. There's two things about it. It's more numerically robust, one. And two, the assembly operation is not adding, which is hard on the GPU because it's synchronization. It's a concatenation. And so it's more parallel, more amenable to these techniques. So we're starting off with a simpler problem, really, even though it's tough enough as it is. Yes?
Are FPGAs and or custom ASICs anywhere in your future pipeline?
Yes.
Up for investigation?
The question is FPGAs and ASICs. Yeah, actually, I've now for about 5 or 6 years been a permanent member of the board of a company called Axelogic, which does that very thing. And they've taken my sparse QR and they're actually creating a FPGA sparse QR. So
sparse matrix into Verilog.
Exactly. Yeah, that's the plan. Yes. Maybe Eric.
Yeah, just a general question about your future plans. So you're kind of talking about the dream of exascale and so on. And so, I mean, can you say something about, when the usual problem in these sparse algorithm, especially here using GPUs, is, you're more and more dependent on the network. The communication time becomes more and more difficulty. So you have methods like these communication avoidance schemes and so on. I mean, I was kind of curious where you see this going and what sort of algorithmic insights you have, or what sort of directions you want to explore.
So the question is about distributed memory. I guess I should have been repeating for the recording. I'm sorry about that. I just thought of that. So the question was, in the future, going to distributed memory computing, how do you hope to handle these problems? There's been a lot of work on distributed memory multifrontal algorithms, and I'm going to leverage that what I'm going to do instead that's going to be different is what happens at the bottom leaf level of the parallelism, if you will, is that I can now exploit the GPU well. And so hopefully I can put more work on a single node and still get good performance. And hopefully then that'll reduce the amount of work I have to transfer between. But yeah, that's the next challenge. I mean,
The problem is, if the GPU is even faster now than the CPU, you're making your problem even harder.
well, yeah, I'm making the problem harder. Communication time is going to be difficult to deal with. Fortunately, with QR, you have the advantage of there's no numerical dependencies in the pivot choices. So just like the assembly is a concatenation, you could then potentially do more overlap of communication with communication. So
You can take other questions
yes,
offline.
other questions offline,
Unless
asynchronously.
it's,
Hey, I'm here. You can leave.
the team is going to be here for another full day tomorrow.
Yeah.
And give the talk at NVIDIA on Friday, if I understand.
Yes. Yes. So I'm going to give this the latter half expanded, minus the poetry. Maybe, I don't know.
All right, thank you very much.
Thank you.